Hey, welcome to our lesson on solving simple trigonometric equations. At least I've chosen to classify them as simple trigonometric equations. Um, we're going to look at the first question I'll ask is what does it even mean to solve a trigonometric equation? And then we're going to go through 6 examples of different trig equations that you might solve. We're going to, in this lesson, sometimes when we solve a trig equation, we're going to look for answers between 0 and 2 pi. Other times we're going to look for all answers. We're going to talk about how you do that. So let's get started. So what does it mean to solve a trigonometric equation? Well, anytime you solve an equation in math, you're looking for the value or values of an unknown variable. In order for it to be a trigonometric equation, that unknown variable has to be inside either a sine, cosine, or tan ratio. So an example of that, one that you're actually quite familiar with, is you're solving a trig equation even when you do something like, say, find the sine of x is equal to 1. Of course, the only solution for that between 0 and 2 pi would be pi over 2 or 90 degrees. So there's a very simple trigonometric equation. They're going to get more complicated though. Sometimes you might have, a cosine, with a tan, minus sine squared x equals 0 or something like that. And we're going to look at it. I'm not sure how well that one actually works out, just making it up off the top of my head. But we're going to look at more complicated equations as well and how we can go about solving them. So let's look at our first example, which should be review for you. Then we're going to add a little twist to it that should be new. Okay, let's look at this first example. Solve for sine x equaling negative root 3 over 2. And we're saying solve it where x is between 0 and 2 pi. So that tells us that we're dealing in radians, not degrees, and that we only need to worry about all the possible answers between 0 and 2 pi, like between 0 and 360. So we're not going to include any of the angles that are, doubles. For example, 100 degrees is the same as 460 degrees. And 300 degrees is the same as negative 60 degrees. We're only going to worry about the positive angles that represent angles when you've rotated around the unit circle just one time. So again, this should be reviewed, but let's just quickly go through how we do this. It's helpful to start thinking about where might this angle be. Well, if sine is negative, one thing we can do is we can use the cast rule to convince ourselves where sine might be. Well, sine is positive in quadrant 1 and quadrant 2, and it's negative down here. So we know that our angle has to be down in this quadrant 3 or quadrant 4. Now, as you know, if you've talked to me, I'm not a huge fan of the cast rule. I think it's kind of cheating. I think you should know that since sine is y over r, and since r is always positive, that the only way sine can be negative is if the y value, which is kind of like the opposite side, is negative, in which case it must be down here. Okay, so we know one of our answers is either here or here. Now look at, since sine x is y over r, okay, we know the y value is negative root 3 and the r value is 2. So in these pictures, I could have a 2 here or a 2 here, okay? And then my y value is negative root 3 or negative root 3, okay? And then this, you'll notice right away, as soon as we have the 2 and the negative root 3, we have one of those special triangles where this side is 1 or negative 1. And that makes this angle in here be 60 degrees or pi over 3 when we're dealing in radians. Pi divided by 3, it's kind of hard to write on the screen, but there it is right there. Now, it's a special triangle. That just means you really don't need your calculator. If it wasn't a special triangle, you just have to solve for using a calculator to figure out what that angle might be. So if this is pi radians, then this angle here, okay, is measured all the way from here. So it goes all the way around. And one possible answer is pi plus pi over 3, which is 4 pi over 3. Okay, or the other possible answer that we might have is for this angle right here, it goes all the way around. It almost goes to 2 pi or 360. So another possible answer would be 2 pi minus pi over 3, which is, of course, 5 pi over 3. just like that. So those are our two answers between 0 and 2 pi. In this next example, we're going to do the same problem, but instead of having x between 0 and 2 pi, we're now saying that x is any real number. So how does that change the question? Well, to start with, it's basically exactly the same. Okay, we can draw the same picture and get, again, the exact same two answers to start. Pi plus pi over 3 or 4 pi over 3. Or x is equal to 5 pi over 3. So that gets us started. Now, there are other answers, though, because every time we go around the unit circle, we get another answer. So I could start here at 4 pi over 3, and then I could rotate all the way around, do like a 360, and still be at 4 pi over 3. I could also do that with 5 pi over 3. Start at 5 pi over 3 right here, rotate all the way around, and still be at 5 pi over 3. And I could do that as many times as I wanted. So as it turns out, we can take these answers right here, and we're just gonna make them a little better. Not a model solution to have that there, but that's okay. We're gonna write instead that x is equal to 4 pi over 3 plus 2 pi. Because what I can do is I can start at 4 pi over 3, and I can go around 360, which is 2 pi, and I will still end up in the same place. Now, since I can do that as many times as I want, I say I can multiply that by k, where k is any integer. K belongs to the integers. Okay, so k can be any positive or negative number. You can start at 4 pi over 3, and then you can add 2 pi, I don't know, 10 times, in which case you'd go around the circle 10 times and still be in the same spot. You could also let k be -1. So you're at 4 pi over 3, and instead of going this way, counterclockwise, you go clockwise one time, and sure enough, you end up here. So any integer there will work. And then I can do the exact same thing with 5 pi over 3. The second possible answer is 5 pi over 3. Plus 2 pi k, again where k is an integer. I'd also like to point out that sometimes when you're solving an equation, whether it be a trig equation or really any type of equation, you might want to consider the graph, the graphical solution, or the graph that shows us the answer. So let's look at that right now too. We just look in Desmos. I'm going to type in y equals sine x, and there is the sine function. Now you should be able to graph this on your own and sketch it on your own. I am going to change my step. So let's do pi divided by 6, for example, so we can see the radians there a little bit better. So remember, the equation that we solved was sine x is -√3 over 2, and we sure got answers of 4 pi over 3 and 5 pi over 3, and sure enough, you can kind of see that those answers, I mean, -√3 divided by 2 is a little less than -1. It's about I believe 0.87. So sure enough, we have an answer in there, and then our second answer in there. Okay, and then when you add 2 pi, you start seeing the other answers that would appear in here and in here and all the way down in negative land. So the graph just kind of helps reinforce that idea. Okay, here's our next example. Solve tan x plus √3 equals 0, again for all real values of x. Now there's a couple things that are new with this equation. One is the simple rearrangement I need to do, and it is quite simple. If tan x plus √3 equals 0, that means that tan of x is equal to the negative of √3, so that very simple rearrangement there. And then again, I can draw a little sketch to think about where tan x might be and possible solutions between 0 and 2 pi. So I could again use the cast rule to help me out here and realize that tan is negative in quadrants 2 or 4 here or here. But I think even better than the cast rule is just realizing that tan is y over x. So one of y or x must be negative to make this negative, but not both. So it's either negative in here because x is negative, or it's negative here because y is negative and x is positive. Of course, tan is positive here because both y and x are negative. So it must be that we're in one of these two quadrants. And so we end up drawing a picture that it looks a lot like this. Now tan is y over x, or you can think of it as opposite over adjacent still. So we have root 3, and in this case -1, or +1 and negative root 3 for our two possible answers. Again, another special triangle chosen here, basically to avoid calculator use. Of course, this is 2. And we have our, again, for this example, the 60-degree triangle, or pi over 3. For our little, we call that a related acute angle. Of course, the real angle is measured from the positive x-axis clockwise, or either here or here. And so if we start thinking about our solutions, we would realize that one solution is, this is pi, take away pi over 3, which is 2 pi over 3. The other first solution is this solution down here would be 2 pi minus pi over 3, which is, of course, 5 pi over 3. And so that's our next solution, is 5 pi over 3. Now, tan is a little different, because we've solved for x between 0 and 2 pi. We haven't considered the solutions that come up again and again and again and again. But tan is a little bit different because, I mean, it's tempting to just say plus 2 pi k here and plus 2 pi k, where k is any integer. And that's not incorrect. It's true. You can start here and add 2 pi and you'll get back to the same spot. Same with this angle here. You can add 2 pi as many times as you want and you'll get back to the exact same location. But notice with tan, there's something special happening. Notice that these two angles are actually pi radians apart, or 180 degrees apart, because they form a straight line. And tan is always like that, because if tan is negative, you're going to have an answer in this quadrant up here, and you're going to have an answer in this quadrant here. Or if tan is positive, you're going to have an answer in this quadrant here, and another answer in this quadrant here. And so your two answers are always 180 degrees or pi radians apart. So we can actually fix this answer up, and we can combine them and say the real answer is that x, or the simpler answer I should say, x is 2. So x is really 2 pi over 3 plus pi k, where k is any integer. And there is a nice simplified version. It's basically a combination of these two. Okay, just the idea that, look, 2 pi over 3 is an answer, and then every other answer is pi, or 180 degrees away, just to keep going around and around and getting different solutions. And that's a special feature that happens with the tangent function, but not sine and cosine, that these two solutions are always kind of across from each other, or 180 degrees apart. Let's take a look at our graph as well, because just like before, we can imagine this solution on a graph, and the idea of us having pi k here and not 2 pi k also has to do with the graph of tan. So let's just take a look at that. So back in Desmos, and this time we're going to graph the tan function, and we were looking for when tan was the negative square root of 3. Actually, what I can do here is I can just write y equals negative square root of 3, and then I actually see that value here. It's kind of like looking at where they intersect. When is tan x equal to negative square root of 3? And so we see that that happens right here, sure enough, at 2 pi over 3. It happens again at 5 pi over 3. Those are the two answers we got so far. And then it continues to happen every pi radians after that. And the thing I want to point out is, remember that this graph has a period of pi. So it's not shocking that we are going to, when we deal with solving equations with tan, that we're going to be having solutions every pi radians apart as opposed to 2 pi. It has to do with the period of the graph. Moving on to our next example, we're solving for the sine of 2x is equal to 1/2. So this is a bit different in that we are looking for, we've got that 2x right there. So one thing that you might be tempted to do is to quickly take advantage of your double angle identity and say that 2 sine x cos x must be equal to 1/2. Now that's a great idea, and it's certainly a true statement, a true equation, but in this case it's not actually helpful. It doesn't help you find x to break it up into sine x and cos x. In fact, if this were the original question, it would actually be more helpful to rewrite it as sine 2x is equals 1/2. So we'll just forget about that. And what we're actually going to do is we're going to solve for 2x just as if it were its own angle, because in a way it is. And if we solve for 2x, then we can worry about what x is afterwards. So we'll solve for sine 2x just as if we're solving for sine x. We're going to draw a picture, think about the cast rule. Of course, we know that we have to be up in quadrant 1 or quadrant 2 in order for sine to be positive. So there's my little picture there with 1 being either the opposite or the y value, 2 being the r value or the hypotenuse, which makes my other side either √3 or negative √3, and my angle must be 30 degrees, or better yet, we're dealing in radians here, pi over 6. Always assume in this course you're dealing in radians. There's very few cases that we don't. And now we can say that, okay, not x, but 2x. 2x is equal to pi over 6 plus 2 pi k, because we need to consider the fact that you can keep going around the unit circle, okay, to get more answers. Or we could say that 2x is equal to, this angle here would be 5 pi over 6 plus 2 pi k, where in both cases k is just any integer, and we say that by saying k belongs to the integers. Now we solve for 2x, so to solve for x isn't actually much more difficult. We divide everything by 2. So divide both sides of the equation by 2, and you get your two answers. The first one being x equals pi over 12 plus pi k. And the second answer being x equals 5 pi over 12 plus pi k. I divide that by 2 as well, where k is any integer. And there are our two solutions to that question. Our next example is a slightly more challenging example to work with. We have 2 sine squared x equals 1 minus sine x, and then we're just going to solve between 0 and 2 pi. So when we have kind of a mess like this, especially with a sine squared and a sine in it, we take a strategy that is very common in math, and that's that we try setting it to 0 and factoring it in hopes that we're able to use the 0 factor theorem to figure it out. Let's see what it looks like here. So I set this to 0. 2 sine squared x plus sine x minus 1 equals 0, just basically bringing these two things to the other side. And then this actually factors to 2 sine x minus 1 times sine x plus 1 equals 0. Let's just think about the expansion to show why this works. 2 sine x times sine x gives you 2 sine squared x. 2 sine x plus 1 gives you 2 sine x. And then negative 1 times sine x subtract to sine x gives you the positive 1 sine x. Negative 1 times positive 1 equals 0. If you're having trouble with that, it's basically the same as if you were factoring, say, 2x squared plus x minus 1. That would factor to 2x, take away 1 times x plus 1. The only difference here is instead of dealing with x's, you're dealing with the sine of x, which is also just an unknown value. Okay, if two things multiplied together give you 0, it must be that one of them is 0. Either 2 sine x minus 1 equals 0, or sine x plus 1 equals 0. Okay, so two possibilities here. Either 2 sine x equals 1 means sine x equals 1/2, or sine x equals negative 1. So right here, we kind of have our two possible answers, and we just need to solve them for x. Let's start with sine x equals negative 1. So when is the sine function equal to -1? Well, there's a few ways of thinking about it. One way to think about it is just imagine the unit circle. There's a very ugly looking circle. Remember that on the unit circle, every point on the unit circle, its coordinates are the cosine of the angle and the sine of the angle. So the sine of an angle could be thought of as the y coordinate on the unit circle. So when is the y coordinate on the unit circle equal to -1? Well, only in one place, and that's right here. Okay, so that answer is 3 pi over 2. And in this case, we're not worried about answers that are not between 0 and 2 pi, because that's what we asked for. Now, don't forget that when you're thinking about when sine x could be -1, that you can also use the graph of sine x. You should be able to sketch this graph pretty easily between 0 and 2 pi, and sure enough, the only point where sine x is equal to -1 is when x is 3 pi over 2. There's that point 3 pi over 2 and -1. So again, using the graphs provide another tool for you to come up with some answers that should make sense. Okay, so when sine x could be 1/2, hopefully we are getting pretty comfortable with questions like that now. So sine x is a half either in quadrant 1 or quadrant 2. Okay, so one possibility is this right here, where we have a 1 and a 2, or we have a 1 and a 2, another special triangle, either √3 or -√3. And the angle that's inside of here would have to be pi over 6. So we either have x is equal to pi over 6, or we have x is equal to pi over 6 short of pi, so pi minus pi over 6, which would be 5 pi over 6. So there we go. We have 3 solutions here, 3 pi over 2, 5 pi over 6, or pi over 6. This answer works, 3 pi over 2, because when this x is 3 pi over 2, sine x is -1, and we get 0 here, times that gives us 0. And then pi over 6 and 5 pi over 6 both work, because that evaluates to sine x as a half. 2 times a half minus 1 would give you 0. So we have 3 answers between 0 and 2 pi. If we wanted to look at answers that weren't between 0 and 2 pi, look at all answers, we have to start thinking about adding 2 pi k to all of those solutions as well. Let's look at one more example. This example, like the last one, involves a bit of algebraic manipulation. And we're also solving this time again for XER, so all possible values of x. Well, we're going to just start with some algebraic manipulation. Perhaps setting this to 0, like the last example, will work. So I bring the cotangent to the other side, make it negative. Now it's set to 0. I start to use some of the skills that maybe we used when we're solving trigonometric identities, and that's playing around with cotangent, for example. I know cotangent is cosine over sine, so I can do that. Now, there's actually quite a few ways that you can manipulate this equation. I'm actually going to do is I'm going to multiply both sides of the equation, because it is an equation, by sine x, because I realize that's going to take the sine x out of the denominator here. Another thing someone might do is bring this term over and cross multiply or something like that. It's all really the same thing. When I do that, I get 2, so I multiply this by sine x to get 2 sine x cos x. I've just written the sine before the cosine. And then I multiply by sine x, of course, the sine x divides out there, and then I love multiplying by 0. 0 times sine x just gives me 0. So I'm left with this equation here, and actually it's going to factor. It has a common factor of cosine. Factor out the cosine, you're left with 2 sine x minus cosine of x times 2 sine x minus 1 equals 0. So if these two things multiplied together, this times this equals 0, then that will work if one of them is 0. So either cosine of x is equal to 0 or 2 sine x minus 1 equals 0, which means our two answers are going to be when cosine of x is equal to 0 or when sine of x is equal to 1/2. So let's look at those. Let's start with cosine of x is equal to 0. When does that happen? Well, again, you could think about the unit circle, okay? And when on the unit circle is in this case, when is the x value equaling 0 on the unit circle? Okay, well that happens either right here or right down here. So that is when x is equal to pi over 2 or 3 pi over 2. Another way of realizing that is to think about the graph of cosine as well. If you sketched a graph of cosine, you would find it is 0 at pi over 2 or 3 pi over 2. Now again, we got to be careful because we're dealing with XER. So really we need to consider all the cases. Now again, we got to be careful here too. Another reason is not only can we add 2 pi to get another solution in this case, but notice these solutions are actually just pi degrees apart. So I don't want to go adding 2 pi k to each of these when really they're separated by pi. So a solution, cosine of x is equal to 0 at pi. Then you could add another pi to get here. You could add 3 more pi's, 1, 2, 3, and get to another solution. You could take away a pi and get to a solution. So starting at pi over 2 or 3 pi over 2. So really, I'm going to actually erase these answers here that I've got. And I'm going to say really the answer for this one is that means that x is equal to 3 pi over 2 plus pi k, where k is any integer. So that's my solution that corresponds to cosine of x being equal to 0. Of course, another solution is going to occur when sine x is equal to 1/2. I mean, we've done that a few times today already. In fact, if you look back at the last example, we found that sine x is 1/2 is pi over 6 or 5 pi over 6. But of course, now we're going to consider all the possible answers, which means that we could have x being 5 pi over 6 plus 2 pi k, or actually, I forgot the first one, pi over 6 plus 2 pi k, where k is just any integer. And there you have it. So in this example, we have actually 3, I wouldn't even say 3 solutions. There's an infinite number of solutions, but there's 3 sets of solutions. At 3 pi over 2, sorry, let me fix that up. Cosine of x, this answer is fine. It's correct, but why I chose to use 3 pi over 2 and not pi over 2 is just a little strange. So I would think it would make more sense to talk about pi over 2 plus pi k. Why 3 pi? I don't know why I would do that, but there you go. So there you have it. That's about as difficult as they're going to get in this lesson, and thanks for tuning in.